As for the spin-boson problems, what the spin-boson model is a two-state system. So it's a system such that we have a continuous degree of freedom. In this case, this paper used the term Q for that. And then it's creating a different potential. And what we see is we see this double minima in the potential. And what you are doing is you have slightly different degrees of omega between the excited and the ground state in these two wells, which is denoted by this epsilon here. And what we see is that if it's isolated from the environment, we get this Hamiltonian here, where this portion of the Hamiltonian is describing the tunneling between the two wells. And this is talking about how they interact within the well. So the one thing to note here, they are using these sigma x and z, which are the Pauli matrices, and they have chose a basis so that the sigma z, the eigenstate of sigma z, will be +1 if the system is localized in this well, and -1 if it's localized in this well. But in most realistic systems, we're going to have interaction with environment, and this interaction can be significant enough to change not only the quantitative but qualitative behaviors. And this is due to a term that takes this form where the sigma z is, again, the Pauli matrix, and the omega is some operator representing the environment. So what you actually get for when it's interacting with the environment is you get this form, and this is what is termed the spin-boson Hamiltonian, which I have color-coded to represent different sections of the Hamiltonian. So this pink color is the system Hamiltonian, which you notice is the same as the previous. This orange color is the Hamiltonian of the bath, and then this blue is the interaction Hamiltonian. So again, we note that we have this tunneling factor, and here we have a factor that's talking about dealing with the distance between here. That's what this Q is this distance. The C, and I guess it just appears here. I thought it appeared one other place. The C is the coupling between the system and the oscillator. And so that's what we get for this. And then if I understand this correctly, we have the spectral function, which can describe the coupling between the system and the oscillators and its dependence. And it depends on the frequency and how the frequency relates to the tunneling factor. So if we get a cutoff frequency that's significantly less than the tunneling factor, it has a power law behavior, which we can see in this equation. And then what they note is that the behavior changes significantly depending on what this value of S is. And without looking at the notes I have on the slide, I don't remember how it changes. But it has a different effect for S greater than 1 than S between 0 and 1. And S equals 1 is the case that is what they called an important case, because it's the point between these two